Okay, good. So let's start again, and again discussing, concluding in a way the first part of this discussion on decision theory. And I would like to conclude with this graph, which makes a summary of the differences between top-down and bottom-up approaches. In particular, the top-down is on the left. You already know what is about. It starts from climate scenarios and goes through the identification of alternatives. In the middle, we have bottom-up approach with example of robust decision-making. As you may remember, it starts from candidate strategies, evaluates strategies against scenarios, and then vulnerability and elaborate and test new strategies. In this category, in the middle column, we could include also InfoGap because the workflow is more or less the same, with differences that get materialized when evaluating strategies against scenarios. So the evaluation is considering opportuneness function and robustness function. So basically, with a small adaptation, also the central column can be used to describe InfoGap. But indeed, there are also studies linked in my web pages where the two approaches are compared, InfoGap and robust decision-making in the context of climate change. There were some review articles comparing the two of them, and there are many similarities, but also some differences related mainly to the fact that InfoGap also evaluates opportunities. In the right, you see another decision-making method that we didn't discuss so far. It's called decision scaling. It was introduced about 10 years ago. It's another kind of robust decision-making, which was called decision scaling because it was introduced in order to identify what is the best scale of representation of future climate scenarios. Because when generating future climate scenarios, we start from the large scale and then we downscale to the regional scale and local scale. And therefore, this method was introduced in order to find out what was the most appropriate scaling option. The difference of decision scaling with respect to robust decision making is tiny. It's a subtle difference. Robust decision making starts from the identification of the candidate strategies, and also InfoGap starts with the identification of candidate strategies. So we have to face a problem, we have to find solutions to a problem, and then we identify first the strategies, and then we use the climate scenario to test the strategies. Decision scaling starts from a different first step. They say that we need to start by assessing vulnerabilities of the system. So not really with the identification of the strategies, but first with the identification of vulnerabilities. What is the rationale behind this? The rationale is that is rooted in the no-regret principle. So no-regret principle means that whatever solution we identify, it should be a solution that leads to no regret, meaning that at least it reaches a target that satisfies minimal requirements. And therefore, the idea is to focus on the current problems, on the current vulnerabilities, like you get an earthquake, and okay, the earthquake is not really related to climate change, but let's suppose that you get an earthquake or a volcanic eruption, and then you have a clear sign of vulnerability, because once that disaster occurs, of course, the disaster can occur again. So you have a clear indication of vulnerabilities, a clear indication of what were the parts of the societal system that were more vulnerable to the event, and then you identify with the future climate scenarios whether these vulnerabilities are confirmed in the future, like if a place is exposed to landslides, you identify through a climate scenario if in the future the landslide risk, which is mainly related to precipitation, is going to increase, decrease, remain stable, and therefore everything is finalized to the identification of vulnerabilities in the future, starting from the current vulnerabilities. Here you see a step further information because the authors recognized that there could be additional information, additional climatic information, helping us to reduce the uncertainty of future climate scenarios. And therefore, it can be like time series analysis, integration of several different methods. And in a way, they admitted that there is a further step to be included, which is additional information that can be exploited by the analyzer in order to reduce the uncertainty on the future climate. When you refer to the literature from the water resources community, usually these people are quite aware that there is a lot of uncertainty in climate scenarios. They are quite aware because they are dealing with practical problems. They are really dealing with water resources in the field. And so they have a good knowledge, a good perception of what has been changed in climate, and have also some sensitivity in order to understand the reliability of future predictions. So this is why it's more likely that you find an advice, an indication of reducing the uncertainty of climate scenarios. And then, after assessing the vulnerability, the plausibility of this vulnerability in the future against our perception of the future climate, we elaborate strategies to minimize the risk to systems. So here you may see that indeed the strategies come as the last step, but there is anyway the idea of starting from vulnerabilities, the idea of starting from a practical solution to the problem. So even if the strategies are placed in the last step, when one is suggested to focus on current vulnerabilities, there is anyway a bottom-up approach, starting from the solution. Okay, they start not from the solution, but from the vulnerabilities. But there is anyway a practical imprinting, an imprinting to start from the bottom, from the needs. So basically, the difference is mainly in the mindset. You could apply all of these approaches to solve the same problem, and probably you will come to very similar solutions, with the differences that are dictated by the fact that you give higher priorities to, in the top-down approach, to predictions, to future scenarios. In the bottom-up approach, to the current situation, and in particular, you may start from solutions or from problems that need to be solved. But anyway, you start from the field, from the technical application. I'm not providing any example related to decision scaling, and I could provide it, and you can find it easily in the literature. There is to say that the literature is not always easy. So the interpretation and understanding the difference between approaches is not always easy, but still it's probably, if you are interested, for sure you will find a lot of application on the subject. I also need to find, and I will give it to you, the data for this exercise that I developed, which you could try to repeat. I will try to update it in the near future. Now, this discussion is basically closed. Let me see if I have further slides or not. Yes. Okay, perfect. And this discussion about robust decision-making in several different forms, it's concluded here. Now I have two more methods that I would like to discuss with you. The first one is very quick, and the second is a little bit more elaborated, but I think we have time today. And these methods are additional methods for decision making that can be structured in a robust framework, but actually, if they don't necessarily need to be structured in a robust framework. Basically, they are, these two methods which I'm going to describe to you, they are extensions of an optimization approach. Even an optimization approach can be structured into a robust framework, but these methods are more conceived in an optimization context rather than robustness. As I said, they can be applied by taking robustness into account, but they are not really defined as robust approaches. I give to you this information in order to try to help you to get an overview, to get an overall picture. So we started from optimization, and then we went to robust approaches, and we discussed basically three of them, robust decision making, info gap, and decision scaling. And then we are going back to an optimization framework and discuss extensions in order to make the optimization framework more comprehensive. And I think I should better start by mentioning the first extension, which is still optimization, but in a multi-criteria context. Optimization, we discussed it very briefly. It consists of optimizing an objective function. We discussed optimization when we talked about linear regression. When we talked about linear regression, we said the slope of a linear regression is estimated by minimizing the sum of the squared interpolation errors. And we said least squares. This is optimization, to be more precise, it's minimization. So it's optimization through minimization of an objective function, which is least squares. And while I talk currently in the blackboard, so what is a logical way of extending mono-objective optimization? The optimal way, the obvious way to extend it is to extend the number of objective functions. So instead of having only one objective function, you may have two. Like, I want to minimize the cost while also minimizing the environmental impact. So quantified in some way. So the environmental impact could be quantified with an indicator. I want to minimize it, but I also want to minimize the cost. And this is not automatic, because you may have costly solutions that optimize the environmental impact, and you may have very cheap solutions that don't minimize the environmental impact. If you think of burning fossil fuels, it's quite cheap, but it has a high impact in terms of CO2 emissions. If you think about electric cars, they are minimizing emissions, supposedly, but they are not cheap. So we may have the idea of finding an optimal solution that minimizes both cost and environmental impact. Let me go with the blackboard, because I think it's easier to make an example. No, it's not a problem, because they are just passing by and they can also make a shout to their colleagues, so it's no problem. Okay, so the blackboard is there. Okay. Yeah. And let be. Okay, so if I refer to a picture, it's quite easy to be demonstrated what I mean. So let's suppose that we have a plane, 2D graph, with the cost in the vertical axis and the environmental impact here. Okay? So you may have a solution that is characterized by a given cost and a given environmental impact. So the solution is this one. And this is solution one. Good. Quite clear. You get a solution like electric cars. Electric cars is not a good fossil fuels, low cost, high environmental impact. It's here. Now, we may have another solution, which is electric cars, which is here. And you may have another solution, which is somewhere here, like here. Okay. And then you may see that there is another solution that is, okay, the solution is here. Another solution that is like higher cost and a higher environmental impact, which is here. Okay. So if you compare this solution with this solution, the solution is optimal in terms of environmental impact. And it's not optimal in terms of cost. If you look at S1, you get a solution that is very convenient for the cost, but not for the environmental impact. You don't know what to prefer between these two. And then let's see S3. S3 has, if you compare S3 with S2, you see that the cost is lower, the environmental impact is larger. You don't know what to choose. If you compare S3 with S1, same thing. Okay, so S1 is better in terms of cost, so what I should choose. If you compare S3 with S4, S4 has larger cost, larger environmental impact. We see that this is, we see that S4 is dominated by S3. So reject S4. Reject S4. If you explore all the possible solutions, you will find some solutions that are dominated, and you exclude them. And you will identify a number of solutions, like in this case, S1, S2, and S3, that are non-dominated. And these are preserved for further evaluation. Those non-dominated solutions are also called Pareto solutions. Pareto solutions. So Pareto optimization means that you work in a multi-objective environment, and the procedure is developed by first identifying the Pareto solution. You can work in any dimension. In the two-dimensional plane, is easy to show what is the concept, but you can work also in 100 dimensions. Of course, not in a graphical method, but with the computational resources that we have, we can explore millions of solutions very rapidly, And we can identify very many objectives. And the identification of the Pareto solutions may help you to reduce the dimensionality of the problem. From 100 possible solutions, you may end up to like 4 or 5 Pareto solutions. And then the choice between the different Pareto solutions becomes a matter of discussion with the stakeholders. If the solutions are described by continuous variables, you identify at the end of the story a line of separation between the dominated solutions and the non-dominated solutions. So basically, there is a region that is a region in the plane, in this case, that is bordered by what is called the Pareto frontier. So basically, it is the boundary of the dominated solution which identifies the non-dominated solutions. So for instance, if you apply this method to parameter optimization, let's suppose that you, for instance, want to estimate a parameter of linear regression, and your objective is not just least squares, but it's least squares plus something else, which may be that you want to minimize the sum of squares and minimize uncertainty, for instance. Then you may get to a sequence of infinite values of parameters, potentially, because it's it's continuous surface to parameters. It's a continuous surface from which you can identify a Pareto frontier, which allows you to reduce, to restrict the number of possible alternatives. This is multi-criteria decision making, it's called. And you see that we are working in an optimality context. It's optimality with respect to several criteria, but still optimality. We can frame it in a robust framework if we allow for uncertainty of some of the information, of the basic information, and then we want, for instance, to estimate what is the maximum tolerable uncertainty in order to reach a predefined limiting performance. This is quite simple. Let me now look at an extension of this, and in order to it's an extension. It's an extension of this multi-criteria decision making, where in this extension we want to give different weights to different objective functions, different priorities. In this case, I talked about cost and environmental impact and give the same priority. But think of a situation in which I really want to give more weight to minimal cost. Therefore, I am in a way, maybe I have to find a way to give low priority to some solutions that are in the upper part of the vertical axis. So give weight to the different objectives. And this is relevant because think of this example here, cost and environmental impact. Have they the same weight? It depends on the stakeholders. So a stakeholder may be more interested in the environmental impact rather than in the cost. A stakeholder may be willing to pay, so willing to spend money to minimize environmental impact. On the other hand, another stakeholder may be not willing to pay because the stakeholder may have less resources, and therefore, when you have few resources only, you usually care less about environmental impact. You take the risk because otherwise there is no progress, there is no innovation if you don't take the risk. So let me talk about this extension and sorry, this is the web page. I need the slides. Let me unpin the blackboard. This is called analytic hierarchy process, and it's a way to attribute weights, to attribute priorities to different objectives in the framework of a decision. There are several methods for doing that. This became quite popular, a lot of popularity in the framework of climate change and environmental resources. First, let me say you have a lot of information over the web on this. There is also a Wikipedia page that is proposing an example, which is a bit different from the example that I'm proposing here now, because I want to illustrate it with an example, again, because it's much simpler, very much simpler. And so my example refers to environmental applications. It was prepared by me, but it is very simple to prepare examples, as you will see. And the idea is that we have to deal with a very complicated decision. It's a decision that involves a lot of complexity. And the idea is that we split a complicated decision into sub-decisions, into simpler sub-decisions. Remember, this is indeed a good strategy. When you face a complicated discussion with people, complicated because it involves around a very complicated problem, remember that complexity generates complexity. So when people don't understand, the discussion becomes more complicated, and then it becomes complicated, and people therefore don't understand. So when you get stuck into such a circular problem, and the best way out is to stop the discussion and say, look, let's make one step at a time. And so one simple step at a time. Okay, this is the idea here. Is you have a very complicated decision. Let's try to split it into very simple decisions. Okay, and this indeed sometimes helps a lot. And the idea is to make it analytic. You see the title, analytic hierarchy process. So we have also to find a way to convert preferences of people into numerical values if we want to structure an analytical framework. And we want an analytical framework because the idea is to use weights to identify the priorities, to identify the preferences for the priorities. And the context is here a discussion among several people. Okay. Let's suppose that you have a discussion in a public forum with a lot of stakeholders. Okay, there is no limit to their number, and therefore the discussion becomes quite complicated. The example I refer to is a water resources management problem. It can be easily extended to, it is actually a climate adaptation problem. So let's suppose that we have to reach 4 targets, the net benefit, which is indeed very often included because resources are always limited. Environmental impact is another. So net benefit is like the cost. The benefit is a larger concept than the cost. The benefit is the difference of income minus cost, and therefore gross income minus cost gives a benefit. It is measured in economic units, usually euros. And then the environmental impact. The environmental impact is something that sometimes is difficult to quantify, and we have to find a way to express it numerically. Okay. And then the impact on the river flow regime, because you will see that alternatives, some of the alternatives may be based on withdrawing and taking the water from the river, and then the CO2 emission involved by the solutions. So we have to find a way to measure these criteria. Some of them are easy, net benefits, CO2 emissions, and we have data, and so we have units. Environmental impact and the impact on the river flow regime is a bit more a puzzle, how to measure these 2 objectives. And also, let's note that we have to compare them. So, I mean, you have to rescale in a way these measurements, because otherwise, how to compare millions of euros with a 10% increase of CO2 concentration? It's difficult. So we have to find a way to make them comparable. So first of all, we use utility functions to rescale and measure the criteria. Measure and rescale the criteria. What is a utility function? It is very simple. Let me go again on the blackboard for a second. Okay, and let me finish. What is a utility function? I think I have a utility function here. Yeah, okay, this is linear. So let's suppose that we apply to the criteria environment. And let's suppose that we have three possible solutions. We will discuss the solution later on. So let's put into a graph the number of solutions, the solutions. Let's put here S, and let's put here the utility U of S. The utility by definition varies between 0 and 1. Okay. So let me make an example. Instead of the environmental impact as an example, let me start from the economic cost. That's the benefit. It's and net benefit. So benefit. Let me start with a criteria that is measurable already through a number. So let's suppose that we have three solutions, and this is benefit one of the first solution, so B1. And here you have a number. Okay. Let's suppose that this is benefit two. Benefit 2, and let's suppose that this is benefit 3. Now, three benefits because we have three solutions. By definition, we give utility 1 to the solution that gives the higher benefit. Okay. We may decide to give utility 0 to the solution with the lowest benefit. Okay. And then we may decide, like it is done in the figure there, to take a linear interpolation between the two. So benefit 2 will correspond to the linear to the utility U2. Okay. So what is the requirement for defining a utility function? So utility must lie to the interval 0, 1. And utility is not decreasing or increasing benefit. And I think there is another condition. Utility 0 is assigned to the minimum, utility 1 is assigned to the maximum, increasing utility, yes, okay. In this case, we assume also that utility is varying in the interval 0, 1, utility 0 is assigned to the lowest benefit, utility 1 is assigned to the highest benefit. Linearity is not the only solution. We can also do something like this. And in this case, if the benefit 2, it is assigned higher utility. Or conversely, we do something like this. This is a convenient way to rescale, to rescale. If you want to rescale the environmental impact, you first have to find a way to measure it. And then once it is measured, it can be rescaled. So the environmental impact will be measured through the price for restoration, for instance, the cost for restoration, or it could be measured also in terms of a numerical quantification by people. You may ask people, for instance, in order to determine the utility of three solutions, the utility associated with the environmental impact, you may ask people to give an estimate of the utility. You first identify the solution with the lowest environmental impact, and this is utility 0. You identify the solution with the, sorry, it's utility 1 with the lowest environmental impact. You identify the solution with the highest environmental impact, utility 0. And if you have a third solution, you may ask people like what is, in your opinion, the utility? And of this solution that is in between in terms of environmental impact. So you give a utility of 0.5, or you give a utility of 0.8 in terms of environmental impact. It could be also pulled between people. And there are also some strategies in order to guide this discussion. Another possibility is that you estimate the cost of restoration, for instance. So the moral of the story is that through a utility function, you can rescale the various criteria in the interval 0, 1. In some of the approaches, people don't start from utility 0 with the lowest performing solution. Sometimes they start from, because they are happy with the solution, even if it is the worst one, they give, okay, let's give a utility of 0.5. This is subjective. It doesn't change much. I mean, my suggestion is to make it simpler to start from 0 with the less useful and give 1 to the highest, and then, because it doesn't change much, and then you classify the others. But this is the moral of the story of the utility function. Now, let me refer to the example. The example is I need to increase water resources availability because I have to adapt to climate change, and I identified 3 solutions. So let's suppose that we are in a robust decision-making context. First, identify the solutions, and then we evaluate them. In this case, without taking robustness into account, but we could. So the 3 solutions are building a dam, reducing losses in the pipeline, and adopt precise irrigation. Precise irrigation is very useful because irrigation takes about 2/3 of the water resources at the global level, of the human use, the human water consumption. And therefore, if you make precise irrigation, some people say that you can save half of it, which means that you save half of 2/3, so 1/3 of human consumption. So it is indeed a good option. Some people don't believe in precise irrigation. And the reason is that, you know, from the point of view of people, from the perception of people, a dam is very effective. Because it's something huge, you see a big lake, a lot of water, but precise irrigation, you know, you don't see anything. So it's less, but otherwise, the problem is that you need a lot of tools, you need a lot of money for precise irrigation, also for the time, but, you know, it's not so, yeah.
In our country, we say the brain of the wise of the people in their eye.
Yeah, of course, yes.
I don't know in Italian or in other cultures.
You said the wisdom?
Yeah.
The wisdom is
the wisdom of the people.
I don't think we have a similar say, but I fully understand the meaning. Okay, let's suppose that we have to evaluate these 3 alternatives with 4 criteria that benefit environmental impact, as I said, impact on the river flows and on shear conditions. Perfect. Now, let's suppose that we already have utility functions for these alternatives, and thus for these impacts, we have utility functions. So we have already measurement of the criteria for each solution. Okay, So, for instance, we say that the net benefit, we call it W1. So we identify the net benefit with the symbol W1, environmental impact with W2, the impact of river flourishing W3, and the last W4. So for each of the alternatives, we see that we have the various W measurements. Okay? The problem is so measured in terms of utility. So for each of the alternatives, we have the 4 utilities. The problem is to find out the weight to give to each of the 4 criteria. Okay, so let's call the weight. Let me see. The weight is called. Sorry, the weight is W, and the symbol for each of the criteria is N for net benefit, P for the environmental impact, R with the river flow regime, and C for the CO2 emissions, like you see in the yellow fields. And we need to give the weights W1, 2, 3, and 4. These are what we need to estimate. And then we have for each of the criteria, so let's focus on N, net benefit. We need to estimate the weight, W1, to give the net benefit. We have the estimates N1, N2, N3 of the net benefit given by each of the solutions. So N1 is the net benefit of the dam. N2 is the net benefit of reducing losses. N3 is the net benefit of precise irrigation. So for each of these solutions, we have the measurement of N, the measurement of E, of R, and C. So for each solution, we can compute the measurement of each criteria multiplied by the related weight. So let me go over the blackboard and let's consider solution 1. It's the time. Okay. Okay. Camera is already over the blackboard. So solution 1 is the dam. Solution 1 is the dam. Okay, we have N1, it's between parentheses, correct? Yes. Okay, N1 plus E1, it's environmental impact, plus R1 plus C1. Okay, so we have the measurement of the net benefit, the measurement of the environmental impact for solution 1, the measurement of the impact on river flow, the measurement of CO2 emission. Now, we have the weights of each criteria, and we multiply the weight times for the dam, the weight for times the net benefit, plus W2 is the second weight related to economic cost, environmental impact, times the environmental impact of solution 1, plus W3 for impact on river flow, plus W4 for the CO2 emissions. And this summation composes what we can call, I don't think I have a simple way, the score of the dam. Score of dam.
So, of course, the weights have different values depending on the importance of this
Yes.
and the solution.
Yes, the open question is how to estimate the weights. I can anticipate that the summation of WI, this is a constraint, this is one. Okay, the summation of the weights is one. Okay. And then we can put in the score of losses, of reducing losses. So what we do is W1 and 2. Did I call it N2? Let's see. Yeah, no, it's not N2, but I think it's N2, yes. It's not explicitly written there, but it's so W2 E2 E2 plus W3. Sorry. So it's net benefit environmentally but correct. So net benefit to E2, yes, W3 part 2 plus W4 C2. And this is the score of reducing losses. And then we can compute also the score of precise. The score of precise, same thing. W1 and 3, W1 and 3 plus W2 E3 plus W3 3 plus W4 C3. Good. And now I take the best score. What are the open questions? But it looks quite simple. Like, okay, I pick the best one. Yeah, define the weights. And just keep in mind that also the definition of the utility function, we didn't go into the details. Here there is an exercise, by the way, which is, we don't develop it today because we don't have time. But if you want to look at the exercise, there is mitigation of full details. So let's suppose that for the utility function we solved it. Still, we said, okay, linear, non-linear, how to measure the environmental impact. There are some open questions, but let's assume that everything is okay. Now, how to estimate the weights? You understand that if you ask people to estimate 4 weights to be given to 4 criteria, and you have a lot of people in the discussion, it's impossible. It's impossible. Let's suppose that you have in the room only 3 people. You have the CEO of the engineering company that is in charge of designing the solution. And of course, you know, the done is attractive because from the point of view of engineering, you know, a lot of money of compensation. Okay. And let's suppose that you have a person living just down the street down, and you know, it's always better not to have a run just in front of your window. And the third person may be a fisherman, like a passionate, militant fisherman, representative of an association, of a sporting association of fishermen, and you know, they don't want the river flourishing to be found. So if you just ask them, give your weight, they will completely differently. The engineer will say, okay, max W1 is great, because the cost of the net benefit, I mean, the larger the cost of the dam, and then the larger my income, and the fisherman will give much weight to W3, river flow regime. It's extremely important. And the owner of the house, he could say, like, what is more convenient to me? Maybe the environmental impact, because the dam is hugely impacting, or it depends on their reasoning, but they don't agree, absolutely. So what is the solution to estimate the weight? It's precisely the ERT process. And the ERT process, the idea is, besides utility, to compare the criteria 1 to 2 by 2. So the idea is to ask people, like, okay, let's split the decision. We have to compare, it's a complicated decision because we have a comparison between 4 things. Let's compare them 2 by 2. So let's ask the first person. So do you think is more important the net benefit or the environmental impact? And then you make a pool between people, and probably they could, to some extent, and it's easier to find an agreement. And then you compare so the first with the second, the first with the third, the first with the fourth, and then the second with the third, and the second with the fourth, and then the third with the fourth. Okay, so for criteria, we use 1, 2, 3, 4, 5, 6 comparisons. And the idea is to compare with, according to this matrix, which was proposed by a guy called Satie. And he proposed to mark equal importance with 1, so people may agree that cost is the same importance of environmental impact, and benefit is the same importance of environmental impact, and they put a 1 there. Okay? Or if they think that the first is moderately more important than the second, they put a 3, a score of 3. If they think that the first is strongly more important than the second, the score is 5. It's very strongly more important, the score is 7. If it is extremely more important, the score is 9 in this comparison. You can use fractions. First, you can use values in between. And you can use fractions. What I mean with fractions, if you think that the first, you compare the first with the second, if you think that the first is moderately more important than the second, I say we give 3. If we think that the second is moderately more important than the first, we give 1 thing. Okay? And you make a comparison, and you can draw a matrix. Here is the matrix, for instance. So let's look at the matrix on the screen. Let me unpin the blackboard. And let me, okay, here we are. Let me, the camera is pointed me. So let's suppose that you get this matrix. So what you do is, first, the matrix, the diagonal is 1. If you compare criteria with itself, they have the same importance. So the diagonal is 1. And then we compare N with D. So we compare the net benefit with the environmental impact. Let's suppose that these people say, okay, it's 7. So the net benefit is very strongly more important. So let's give a score of 7. The immediate consequence is that when you go in the second row, first column, where you compare E with N, is the opposite comparison. The score is 1/7. Is this clear? Okay, good. So now let's compare net benefit with river flow. Okay, we give a 4. So the net benefit is I don't remember, like strongly more important. This means that when you will compare the river flow with environmental impact, look here, it looks like I gave more weight to the river flow than the environmental impact. So let's try to take it into account, but it's not needed now. Now, third comparison. net benefit with CO2. Okay, fine. Okay, let's go to the second row, 1,7, because I already determined the comparison previously. 1, it's in the diagonal. Now I have to compare environment with the river flow. And I should take into account what I said before, but let's suppose that, you know, we cannot be rigorous. Let's anyway give a 4, because we said that river flow was more important, and here we make a mistake and we give 4, okay? And so this is a bit of contradiction with respect to the first row, but let's forget about it, okay? When we discuss with people, we don't have really to make the reasoning more complicated. Let's take what comes out, okay? And then we have to compare the environmental impact with the CO2, and let's say that they say, yeah, 1/3, okay? And then we go to the third line. So 1/4 was already given, and 1/4 was already given. It's only missing the comparison between R and C, river flow and the CO2. Let's put 1/3. And then I think with the last line, we are already done. Let's see, yes. And yes, we are already done. The last line is automatic. It's already compiled with the reciprocal. Now, of course, there is an approximation because we already noticed that we have not been very coherent. Now, how can we check if the matrix is coherent? This is nice because indeed this method, being analytically formulated, allows me to make a check. Allows me to check if the matrix is consistent. And what I have to tell people is that, look, there is a mathematical demonstration, mathematical procedures that says that we were not very consistent. So we have to go back to our decisions. How to make this check? First, let me say one thing. Once that you inputted this matrix into R or MATLAB, the check is very simple. So it's not complicated to make the check, but actually to explain, to provide the proof of the correctness is not easy. And I tell you how to do. It can be proved, basically, that the weights are given by the values in the matrix principal right eigenvector. So you may remember something of matrix calculus. So basically, a matrix, you can compute eigenvectors for a matrix. And there are several different eigenvectors. You have to take the right principal one. And the eigenvector is composed by its vector values. You have to rescale them so that their sum is equal to 1. And these are the weights, okay? And the weights can be computed for any matrix, even if it is not consistent. So it's important to check that the decision is consistent. And in the ideal case, it can be proved of a fully consistent matrix, the maximum eigenvalue, lambda, should be equal to the dimension of the matrix, 3 in the above case, or 4, I think it was 4, should be then lambda, the maximum eigenvalue lambda should be equal to the dimension of the matrix. I think it is, here there is, I forgot something, -1. So it is indeed 3 in the above case. And it should be, or let me see. No, it's 4. Sorry, it should be 4 here. Okay, so the eigenvalue should be equal to the dimension of the matrix. So let's compute this quantity here called the CI. So you get the max eigenvalue, which should be equal to the dimension of the matrix, minus the dimension of the matrix. And this is a measure of inconsistency, because it's the difference between the theoretical value and the real value of the eigenvalue. It's a measure of inconsistency. You divide it by n minus 1, and then you obtain this statistics CI. And then you can compute a consistency ratio has this value, so Ci divided by a reference value, Ri. How to compute the reference value? It is quite easy. You generate a random matrix with the only condition that is antisymmetric. So in the opposite position, you have to get the inverse of the corresponding value. I hope antisymmetric is the correct way of defining it. And ones in the diagonal. So basically, you respect the structure of this matrix in the sense that in the opposite position with respect to the diagonal, you have the inverse of the corresponding values. You have ones in the diagonal, but apart from respecting these conditions, you generate the matrix fully randomly. And then you obtain a reference value like of a matrix that is absolutely not consistent. And this reference value, you compute it with the Ci. So basically, if this ratio is 1, it means that your Ci is representative of a matrix that is not consistent. And then there is a table here. And there are suggested values, max values, for the statistics Ri. Ri is, it's already given for the matrix. You don't need to make the computation. This is the value. So if CR is less than 0.1, you can take the matrix as okay. And if it is greater than 0.1, you have to tell people, let's start again with our comparison. Okay. So I hope you got it. So sorry. If the matrix is fully consistent, you get in this computation of CI, at the numerator there is 0. Okay, so because lambda max is equal to n, and therefore Ci becomes 0. Okay, and then you compare Ci divided by Ri. Ri is representative of a matrix that is absolutely not consistent. So if this ratio CR is 1, it means that the matrix is the same as a matrix that is absolutely not consistent. If CR is 0, it means that Ci is 0, and therefore it's fully consistent. And then you compare it with this condition. If CR is less than 0.1, then the matrix is consistent. Okay, what is the weak point of this? And once that the matrix is consistent, you compute the weights as the eigenvalues. What is the weakness of this method? The weakness is that when you come to explain the procedure to people, they have to trust that your method for checking consistency is okay. I mean, it is quite easy to provide a demonstration to people, but you have, when you manage the discussion, you have to grasp, to detect during the development the reasons for inconsistency. Like, for instance, here, if you look at the first row, you see that if the cost, the net benefit, is much more important than E and less important than R, it means that you are giving more importance to R than to E. Correct? Because if you say N is much more important than E, N is more important than R, it's weaker the second. It means that R dominates over E. So when you go to the second row and you see people saying, I compare E with R, you have to gain an expectation, like these people should say that R dominates E. If they say E instead here from this matrix dominating R, you should first conclude this matrix is not going to be consistent. So you have to realize it during the development of the process, keep it in your mind, and you have two choices. Either you suggest to people, look, in the previous laws, you said this, so let's correct it. You can do it online. Or when you make the demonstration and the matrix turns out to be not consistent, you have to be really a solution to tell people, like, okay, the mathematical demonstration, I'm not discussing it with you. I tell you that mathematically, I know it's not consistent, and I can explain to you the reason, and you make the example. But this requires a full control of yourself of the discussion. And this needs a preliminary preparation. Like I have to prepare myself any time I give this lecture. If you go in front of an audience, it's even worse. You have to get very well prepared on the problem and prepared to attend the process. This is the role of the mediator. The mediator has to be very attentive, very respectful, and always find the way to make people understanding that the procedure is correct, where is their limit in the judgment. And remember that this kind of discussions virtually, they usually don't work. And it's, virtually is a bit of a problem. Usually it's face-to-face is much better.
Seeing dominate is less important, right?
Yes, yes, and I use dominated. Let's forget about the use of domination that I did with the Pareto frontier. Okay, but here I wanted to say less important. Okay. So there is, as I said, an exercise that you can. It's very easy actually, and there are the codes in my website available. The exercise is here. First, let me see if I said everything. Okay, this is the exercise. Yes, I said everything. And the exercise is here. Computation of risk associated. No, it's not here. Let me see. I'm sure that there is. So let me see this one, which I don't remember. What kind of exercise is this? I think it is. This is the utility function. No, vulnerability exposure. This is the risk. Okay. I think this is the wrong link. I have to check it. Let me just make a check. I think Okay, let me check the correct link. One second. Let me change one. Okay. Okay, I have to go back again. Okay, I think it's here. Must be here. Okay, certified analysis application reservoir. It is here. I need to update the link. I will update it. And here it's the exercise with the R code. Economic benefit, impact on fish community is a bit different, but it's 4 criteria. And there are the utility functions. And then there is the R code, which is here. And it's quite a simple R code, which you can, if you're interested, you can see. For the exam, you don't need to look at it, but I will put the link there. So you will find, starting from tomorrow, besides the videos of today, let me just go back to our webpage. Okay, you will find here in red this link, Design of Climate Change Adaptation Actions. We didn't discuss this. I put it in red. And here you will find a second experiential learning, which is the pairwise comparison, which I need to link here. This is the computation of risk that we did previously. and I needed to put here the pairwise comparison. Let me check if it is in laboratory. Maybe that I put it in the lab. Maybe, let's see. Yeah, it's here. It's computer, no, trend analysis, no, it's not here. I put the link in both the pages. Okay, now, given that we have some 10 minutes, let me just try to make a summary of what we discussed in order to provide some indications for the exam, okay? It's just a resume. And so we discussed the lectures, which you see in blue, but the last one, okay? Let's go along them one by one. So this was the introduction, and give it some time. These were the slides. Let me open in Google because I don't understand why we don't see it. Oh. Okay. I'm just checking why. Let's see why we don't see it except change introduction. Doesn't work. This is a bit of a problem. I will try to solve it. So let me see if I can find it somewhere else. Otherwise, I tell you just. Before going there, let's see here.
Introduction related to the numbers of the conversion between
Yeah,
right.
yeah. But I don't understand what is the reason why it's not visualized. Okay, I need to inspect it. I will propose a solution for this. Let me. Okay, I will make it available. Anyway, the introduction was related to the numbers of climate change, and from this, just a second, from this lecture, you have to remember the numbers like there was an indication of the CO2 concentration, and there was an indication of the total population of the Earth. There were some indications about the range of global warming, so the temperature that has increased like 1 degree or from the pre-industrial. So try to focus on the numbers because there could be some questions in the quiz like how much is increased the temperature from the pre-industrial level? 0. -2 degrees, +10 degrees, and between 1 and 2 degrees. And of course, you have to identify the correct one. I will, as I said, I will try to understand why it is not visualized the presentation, and I should manage it. And okay, let's go to the second then. The case study, Strait of Messina Bridge, there is nothing that you have to study for the exam. Okay, this is just a description of the case studies, the case study that we have considered, but you have to forget about it. Okay, here there is nothing that you have to learn for the exam, I mean. And then for getting, I mean, your CV done, yeah. Climate impact in civil engineering, let's open it and let me try to see if there could be some questions. And this referred to this PDF. Let's take the slides. Okay. 1 second.
Proprio in your discussion, there could be a question related to the case of Mrs. Rachel.
No, at the exam, no. Okay, here, let me see if there is something. If you see something quantitative here, just
Right in the range.
yes, there are some writings here. And here, I mean, I don't see anything that is particularly, of course, you have to know the definition of weather and climate. It's given also in the introduction. And you have to know the definition of what is climate change. And so basically, you have to refer to statistics, change in statistics. And then here there is once again the global warming, so order of magnitude in the global warming. And then definitions of probability. What is probability? I think we talked about Kolmogorov actions. And you may find some questions related to the definition of probability density and cumulative probability. So like, what is the difference between cumulative probability and probability density? And the correct answer is the cumulative probability is the integral of probability density. And you could find some other options that are clearly wrong, okay? Usually in the questions, it is quite easy to understand if you have got some experience in the topic. It's easy to distinguish what is the correct answer. But please try, and I give you the solution, the recommendation before starting the quiz. Read the question very well, because sometimes there are questions that are the same question, but there is a negation. And you have to, okay, you have to understand, because sometimes I need to prepare a lot of questions, and sometimes they are the same question with a negation. And I see that sometimes the students, they don't, they get trapped into the, you know, I don't know how to say in English, into the tricks. And just take your time, because, and I'll tell you before you start, half an hour for 30 questions is plenty of time. There are many students finishing in less than 15 minutes, because some of the questions require just 5 seconds, the time to open the question, read it, and think, and that's it, okay? And of course, you have to use some strategic moves. I'll explain to you, like, you realize that a question is very long to read. It takes like 15 seconds to read. You can jump it maybe and go to the next one. So you have to first reply to the questions that are very easy. In this way, in 5 minutes, you get 20 questions answered, and then you have like 25 minutes for 10 questions. So it makes you more relaxed, because some of the questions indeed require a careful reading. And you have to identify immediately what is a question that is very easy to read and very easy to answer, and a question that requires a careful reading. And of course, we try to make a mix. And so let's see. Sorry? See, what do you mean? You can, okay. We are. You know, there is the problem that we are getting further instruction for artificial intelligence. So basically, so you can use printed notes, it's no problem. But in terms of internet connection, you could only be connected with the UL. You can't go to my website, because otherwise it becomes impossible to check. You can bring your tablet, but offline. Okay. Okay.
So I can, for example, when I write in summary, I
Ah,
can
yeah, just one
bring it
second,
or
because, sorry, Leah, because I didn't check. I hope you got the audio well. I didn't check. Just give me 1 second, because I can't hear you. Okay, try to speak again.
okay now.
Yes, perfect.
Okay, perfect. So for example, when I write a summary, I can and I print it out, I can bring it to the exam.
Yes, yes. A printout is perfect.
Okay.
And I just said also a tablet offline is okay. So if you save it on the PDF on your tablet and it's offline, it's okay.
Okay. Okay, perfect. Thank you.
Yeah.
The exam will be held in the computer online or not in the paper just with you?
No, the exam is online and you have to bring your own PC and it is very easy. I mean, because the system, the platform can run even on a very old one. So you have to bring your own PC because we don't have a PC room. I can borrow one laptop, but not more than one. And but with this PC that is connected, you can only stay on the web page of the exam, okay? And if you bring an additional laptop or offline or a printout, it's perfect. I personally prefer a printout, but I don't want to make you, I mean, I don't want to make the things more complicated than they are, okay? I would say that the remaining of this document here, which you see on the screen, is more related to the discussion we may have at the oral than to the quiz, because the quiz is for very quantitative questions, you know. Okay, so let's go back to, there is an important lecture is given by, okay, the Earth system. I think there is not much to be asked here. And at least not in the quiz, I mean, in the oral, yes, but, yeah, the definition of linearity and non-linearity may be asked in the quiz. What is a tipping point may be asked into the quiz. Okay, of course, there are tipping points. Okay, and in the quiz or in the oral, I may ask what is a deterministic model, what is a stochastic model, what's the difference between the two. Okay, and Reynolds transport theorem, forget it. Okay, but I may ask what is a conservation equation in the oral, or give me an example of a conservation equation. And you may say conservation of mass, perfect. So what does it mean, conservation of mass? So this is something that may be asked at the oral. The linear reservoir, I don't think we did it, so let's forget it. Okay. And climate models, I mean, let's open it, but I don't think for the quiz there is much. For the oral, yes. And here now the figure are not appearing, but just because of the network. And I think maybe also network problem, the fact that I couldn't visualize earlier the introduction. So input and output for the model, yeah, nothing really, model emulator. Climate models, let me see, no. Okay. Anyway, for climate models, there is not much to say. For risk-based adaptation design, yes, this is material for the quiz. The risk equation, it's a very classical question. Can you please write the risk equation? Explain what is, and in the quiz, there are several questions that will be what is vulnerability, what is exposure, what is hazard, and be careful of the definitions because I tell you statistically, a lot of students make it wrong. Definition, what is vulnerability, what is exposure. I think the reason is that they assume it's very easy, and you know, when one assumes it's yeah. Okay. So be careful because this is, of course, one of the few things that we really studied in detail, and also definition of probability. I already mentioned it, etc. Then there is climate change and water to skip. Inductive and deductive estimation, I don't think here there is much. Let's see. Trend analysis, yes. Trend analysis, linear regression, you could find some questions related to this. So linear regression, linearity, run theory, you may find something. Okay, we said that long-term persistence is to be skipped. And I think here there is, yeah, bias rainfall runoff modeling. I think we did the rational formula. and be prepared on the rational formula, yes. And we skipped, I think, the linear reservoir. Correct me if I'm wrong. We skipped it. So given that we skipped it, you don't have to expect questions at the exam. And then there is decision theory, what we basically describe the info gap. You will find questions about info gap, and please, given that this is analytical, let's try to be prepared on this. Okay. That's it. And if you have any question, for sure, let me know and we can get in touch by email. Okay, Leah, sorry, I stopped it. Let's keep in touch, and if you need any clarification, and the call will be visible on Alma Esami, I hope, beginning of next week at the latest. Thank you very much.
Okay, thank you. Bye.
Bye.